Hello everyone. Continuing to our next part, Chapter 3, Advanced Material Design Challenges and Solutions for LEDs. PE-LEDs, perovskite light emitting diodes. The chemical formula for perovskite is ABX sub 3, whereas the A plus is the monovalent inorganic organic cation, for example methylammonium Ma plus, and CH3NH3 and CHNH2, and also for meridinium Fa plus and cesium Cs plus. For the Be2 plus, which is a divalent metal cation, for example lead Pb2 plus and tin Sn2 plus, whereas the X negative is the halide ion, for example chloride, bromide, and also iodide. The optoelectronic properties for perovskite is very attractive, which is narrow emission line width, high absorption coefficient, readily tunable emission wavelengths covering from ultraviolet to near infrared, and it has a wide color gamut, high charge carrier mobility, and it is a solution processable materials, which is actually translated to simple processing from the precursor solutions that contain raw materials such as AX and BX salts. The deposition method. There are two main methods typically used in perovskite material deposition, that are solution processing and also vacuum deposition. In addition, the combination of solution and the vacuum deposition is also been used. Here, solution process is most used in the synthesis of perovskite-like compounds in CS-PBBr system, which is CS-PBBr3, CS-PB2BR5, and CS4-PBBr6. Solution processing method have the advantage to be fast and easy to process. Moreover, of course, they are low cost and compatible to roll-to-roll device production. In one-step coating, spin coating, the most commonly used in deposition method. In one-step deposition, both precursors are blended in the same solution with solvent like gamma-butyrolactone GBL, and then dimethyl formamide DMF, and also or dimethyl sulfoxide DMSO. The perovskite film is then achieved by spin coating and the foam solution on the substrate film, followed by immediate annealing at temperature above 320 degrees C to form the black phase. As for this two-step spin coating, or into diffusion method, it consists of preparing the active inorganic perovskite material in two different phases. For instance, in a classic two-step spin coating for the preparation of CH3NH3 film, this layer is spread by spin coating or soaking in an early PBL2 deposited on the surface on the substrate. This method is also produced CSPBBr3 also. First, it was spin coated with a PBBr2 solution, which is a mixture of PBBr2 precursor with DMF solvent. After annealing the first layer for a few minutes, the CSBr dissolved in methanol was spin coated to form the result of inorganic perovskite CSBBr3. This method was basically developed to improve the control of the perovskite crystal formation and also the growth. These are the example of different types of structure for perovskite materials. For example, A is the 3D polycrystalline perovskite emitter. As you can see here, this crystal structure consists of ABX, followed with a two-dimensional polycrystalline perovskite emitter, and quasi 2D perovskite emitter, which consists of inorganic and inorganic layer and organic layer sandwiched together. And C is the quantum dot perovskite emitter. For 3D polycrystalline perovskite emitter, CH3NH3 PBr3 perovskite is most generally used in PENETs. Advantages for this 3D polycrystalline perovskite emitter are higher S stability in compared to the CH3NH3 and PBI3, and it has higher PLQE, higher EV, about 76 or 150 MeV. The EL efficiencies of CH3 NH3 PBBR3 PE-LED were enhanced from 0.1% up to 8.53%. However, for this type of perovskite emitter, the thermal stability and stable humidity of CH3NH3 PBBR3 remains quite moderate. However, the solution is to replace or mixing Ma with smaller radius Fa of CS, which resulting in the enhance the tolerance factor T and octahedral factor, which we can be called U for the perovskite, which contribute to gaining more stable perovskite structure. And also another solution is to doping of Mn2 plus in CSPBS PBX3, that is significantly improve its thermal stability and also this fabricated air stable for PLEDs. For 2D polycrystalline perovskite emitter, the structure of 2D layered perovskite is L2AN1BNX3N+, whereas the L is the large organic ammonium separate, the corner-sharing BX6 octahedra that form the organic inorganic overlapping hybrid perovskites, whereas the small cations of A, such as Ma, FACS, or others, can be filled in the coordinated hole if the number of A cations is larger than L, which is n equals to infinity. The 2D layer structure changes to a 3D level structure. The synthesis of 2D polycrystalline materials is similar to the 3D halide perovskite. Actually, the 2D perovskite materials is more stable than the 3D analogs. The advantages of their film forming capability via solution process. However, these advantages are the conductivity of this kind of 2D materials is typically very low due to its intrinsic multilayer quantum well structures surrounding by the insulating long organic ammoniums. For quasi-2D perovskite emitter, it is composed of different number layers of both 2D and also 3D perovskite. This combines the advantages of 2D and 3D materials, which can be summarized as high binding energy, a good film forming property, high conductivity for sure, and enhanced stability. And it is relatively known for achieving high stability. For quasi-2D perovskite material, by replacing Ma in part with the C6H5, CH2, NH3. This can achieve up to no degradation up to 40 days, even in atmosphere under high humidity up to 52%, which is very attractive. The perovskite quantum dots is a same crystal structure as polycrystalline films. However, the quantum dots have more homogeneous grain size and shape compared to the crystal structure of polycrystalline films. The small grain size of perovskite quantum dots could bind these electrons and holes into excitation for a radiative emission, resulting in a very high PLQYs. Synthesis method for perovskite QD are quite relatively simple. For example, the first template both growth strategy, the template of 50% mesoporous Al2O3 mixed in precursor solutions of perovskite demonstrates a small MaPBBr3 and QDs with the PLQY up to 40%. And the second one is the hot injection method. By injecting the mixture of solutions of MeBr and PBBr2, the oxyaluminum bromide away with warm oleic acid and octadecene solvents can produce up to 6 nanometer quantum dots dimension with the PLQY up to 80%. The operational lifetime for PE LEDs is actually working conditions is still low compared with the well-established light emitting technologies of QLEDs and OLEDs. To evaluate the operational lifetime of PE LEDs, a commonly used method is to measure the time elapsed for the devices decaying to 50, 80, or 90% of their initial EL intensity, or can be seen or EQE, which can be defined as L50, L80, or LA90 respectively. These are the summaries for the operational lifetime of the representative reported PE LEDs. So for example, the first one, for a prescribed recipe of MAPBBR3, this device structure consists of ITO, TiO2, EAMHP, SBPO2T, MOO3AU. The operation condition of 120 candela per square meter at 4.8 volts. The operation lifetime here is about 55 hours in atmosphere. And compared with the CSPB BR3 nanoparticles and Ps, with the device structure of ITO, P.PSS, poly-TPD, PFI, MHP, TB, BI, and IF and AL, the operation condition at 5 volts, its lifetime is very low, which is around 10 minutes only. Subsequently, CSPBBR3 CSBR with a ratio of 1 to 0.4 ratio. The device structure consists of ITO, P.PSS, MHP, B3PY, MPM, CS2, and CO3, and also aluminum. The operation condition were in 100 candela per square meter at 66.67 milliampere centimeter squared square meter. So the operation lifetime is for around 15 hours, and followed with a CSPB-BR3 PEO-PVP with a ratio of 150 and 5 weight ratio. The device structure is very simple. It's ITO, MHP, and also gallium. The operation condition also similar with the previous one, with the 100 candela per square meter at, however, with a very quite high voltage at 2.7 volts in compared with earlier. This operational lifetime, however, is only slightly higher than 1 hour. For the recipe of NMEI FAI PBI2 with the molar ratio of 2, 1, and 2, for the structure is ITO, zinc oxide, PEIE, MHP, TFP, and MOOX, and also AU. The operation condition at 10 milliampere square meter. The operation lifetime is around only 100 minutes. Following with the CSP BBR3 NPs, the device structure of AU, P, MG, NIO, MHP, PMMA, and NMG zinc oxide and plus GaN. The operation condition is around 30 to 50% of RH. At 10 volts, unencapsulated and under ambient condition, the humidity is around 30 to 50%. The lifetime is around only 9 hours. So for BAI-MAPBI3, which is a ratio of 20 and 100 NIR, the device structure of ITO, poly, TPD, MHP, TPBI, and IF and AL, the operation condition of 3 milliampere centimeter squared. The operation lifetime is around 300 minutes. BABR-MAPBBR3 with a ratio of 20 and 100. So the device structure ITO, PVK, MHP, TPBI, and IF and aluminum. The operation condition at 3 milliampere, similar with the previous one. The operation lifetime is around 48 minutes. And MAPBBR3 with the device structure of ITO, P.PSS, MHP, TPBI, and IF and AL. The operation condition at 6.5 volts. Also, the lifetime is relatively quite low, only less than 1 second. FA 0.80.2 of CS and PBBR3 and Bs with the structure of ITO, P.PSS, TFP, MHP, TPBI, LIF, and aluminum. This duplication condition is not reported. However, the operation lifetime is very low, which is around 80 seconds only. For the MAPBI3 with the structure of ITO, poly-TPD, MHP, TPBI, and IF, and aluminum with the operation condition of 3 milliampere over centimeter squared. The EQE is larger than EQE initial for around only 300 minutes. And the MAI CSCI PPI with a molar ratio of 2 to 1 and 2, which is a red wavelength. In the ITO, zinc oxide, PEIE, MHP, TFB, MOOX, and also RM at a condition of 10 milliampere centimeter squared. The operation lifetime is around 5 hours. So based on that table that I mentioned earlier, the problem for perovskite is actually the stability in the atmosphere. So we have to engineer the perovskite materials. So tuning the composition of perovskite active materials is alloying to the perovskite active layer with enhanced thermal, light, moisture, and also crystal structure stability. The quantifiable Goldsmith tolerance factor, which is called TF, is an empirical index to evaluate the structure stability of the perovskite crystal, whereas Ra, Rv, and Rx are the radius of the A side cation, B side cation, and halide anion respectively. TF value ranging 0.8 to 1.0 is favorable to form a cubic perovskite structure. Out of this range is actually the non-perovskite structures. So the first method for this type of engineering of the perovskite active layers is tuning composition of perovskite active materials. So the TF values of the pure CS PbI3 and Fa PbI3 are out of the favorable region, which is 0.8 to 1, right? So as you can see here, introducing mixed cations or at the A side, for example, using CS with Fa and also CS, Fa, and Ma, can effectively tune the TF value into more stable region and improve the structure stability of the resulting perovskite produced. In addition, the further embedding the rubidium Rb into halide perovskite films would extend the working lifetime itself. Mixed cation perovskite have also demonstrated as one of the effective methods to improve the device efficiency and also stability of PE LEDs based on the active layers that are processed from nanocrystals and precursor solutions. The second one is to improve the film quality of the perovskite active layers. So the film morphology of the active layers plays a critical role resulting of the final device performance. The much thinner the perovskite films, any discontinuous pinholes would result in possible leakage of current, which may deteriorate the device operational stability. Strategies such as controlling the film deposition conditions, incorporating additive and tuning the surface properties of the substrate. So this is an example of this cross-section of MAPBBR3 films which performed in a different annealing temperatures. Room temperature 60 degrees C, 80 degrees C, and 100 degrees C for 2 hours. It is also can be seen here through the improving quality of the perovskite active films. You can see the surface scanning electron microscopic images (SEM) for the perovskite films with different kind of additives. So this one E is the CS with the additive of CSPBBR3, F is the CSPBBR3 PEO, and also G is CSPBBRT PEO and CEF. And the bottom figures shows the AFM, atomic force microscopy images of perovskite films deposited on different substrates. For example, here H is the substrate of PVK, I is PVK, and also PVN, which is the poly 99bis30 NN dimethyl amino, polypropyl 27 fluorine, L2799 diactylfluorine, and also J is the poly TPD and PFN. Micro light emitting diodes. So this is a brief history for the micro LED's evolvement from starting from the display technology of CRT, which was first introduced in 1950s. This is using the fluorescent screen technology, followed with the early 2000s of research progress with the LCD and plasma display panel. You remember the plasma TV, which has a very thick back end of the television. And also in recent years, the technology utilized was OLEDs and also LED displays. So now the future is actually mini LED and micro LED. However, if you notice now, actually we have the mass production, I think by LG, that uses micro LED. which is quite interesting. So the difference between these kind of technologies, actually, CRT, it has an excellent visual depth and feel, and also have a higher response rate. LCD, the advantages are it can reduce costs and improvement significantly in performance compared with CRT for sure. However, the disadvantages are it has a slow response time, which is the FPS, if you are familiar with it. And LCD has a low color saturation and also a poor conversion efficiency, whereas OLEDs has the advantages of self-luminous, high contrast, wide viewing angle, pulse saving, and also fast response. However, the disadvantages are is this limitation in production. So if LED use a pixel of a display size, its size needs to be reduced according to the desired solution. Therefore, mini LED and micro LED were introduced. These are the size definition of these three character of LED's dimensions. So the first one is the conventional LED. Conventional LED, the size of the LED is larger than 200 micron. Mini LED, the size ranges between 100 to 200 micrometer. And also for micro LED, the size is less than 100 micrometer. The LED attractiveness or the advantages are it is mainly applied to large road display. It is power saving for sure, and it has a high color saturation, and of course it has high brightness. As you can see here, there's a comparison between mini LED and micro LED. The size, as I mentioned earlier, the purpose of mini LED is for the backlight for LCD, and also for micro LED. The purpose is actually itself utilized as self-emitting display. Mini LED has a high dynamic range and power saving, and very thin. Micro LED has high contrast, high efficiency, high resolution, high response time. The yield for mini LED is higher than 80%, which is important for the mass production. However, for micro LED, this is hard to estimate. It depends on the fabrication process. The application for mini LED is mentioned earlier, the LCD backlight from small to large LCD panel. For micro LED, you can use it as a micro projection display from small to larger size if you stack together. Micro LEDs is first fabricated by Texas University in 2000 with a diameter of 12 micron. The application of LED depends on the chip size as mentioned earlier. So the conventional LED we use as general lighting, display backlight module. For mini LED we use as a backlight application, for example HDR and flexible display even. For micro LED we can use it for wearable watch, mobile phone, AR and VR, micro projectors, high-end TVs. Micro LEDs can be combined with flexible substrates to produce flexible characteristics like OLEDs. The properties of micro LEDs is reduced power consumption, high brightness and contrast, high current density operation, high modulation bandwidth, and increased optical power density. So the fabrication and design challenges for this kind of micro LED is actually the first one is RGB micro LED with a full color display. Of course, you have to understand that with each of the micro LED devices, these devices have to emit RGB, all three red, green, and blue light. The RGB full display principle is based on these three colors and can be combined to create all the variety of the colors. It depends on a certain ratio rate setting. The different current applied to control the brightness as for the three primary color to achieve the full color display. So we can change the colors based on the current that we apply. The RGB full color display, each pixel contains one set of RGB micro LED. So this is an example of one set of RGB micro LED. In one same substrate or device, we have all three LEDs, which is red, green, and blue. However, micro LEDs suffer from the drawback in mass production. As mentioned earlier, it's hard to estimate. For example, to produce a 4K resolution display, 25 million micro LEDs is needed to fabricate on a single substrate without any error in the most efficient and economical way. It is hard to transfer and grow the huge numbers of the three colors of micro LED with a placement accuracy of 1 micron or less. So as a solution, All RGB micro LED composed with the same material, same substrate, with same behavior, and also with the same driving condition. However, to find one material that's spanning from the blue to red spectrum all across is quite difficult. In theory, indium gallium nitride material can cover entire visible range by adjusting the indium content. Unfortunately, high indium causes lattice mismatch between GaN buffer layer and in-GaN quantum well. So, to overcome this mismatch lattice, in-GaN pseudo substrate was first introduced by Evan. The substrate has a top relaxed in-GaN layer for full in-GaN LED growth. The in-GaN structure growth has on in-GaN or substrate could produce spectrum span from blue, which is 482 nanometer wavelength, to red, 617 nanometer wavelength. With this technology, we can enable the growth of all LED colors on the same substrate, dramatically reduce the fabrication cost of the whole micro LEDs. The second challenge to achieve full color conversion for full color display. Full color display achieved by employing excitation sources such as UV micro LED or blue micro LED. So these two can be used to achieve this kind of full color display. However, both of these needs a color conversion materials such as phosphor and quantum dots. So for example, this one is the blue LED micro LED or blue micro LED. So this one we use red phosphor or quantum dots and green phosphor quantum dots without the blue ones because this is blue. The other one is using UV LED, so we have to use all of this colored phosphor, starting with the red phosphor, green phosphor, and the blue phosphor. So this is the method to achieve this full color conversion of a color display. So the materials, such as the phosphor, it can emit light for a specific wavelength under the excitation of blue or UV LEDs. It materials determine the color of the phosphor. Okay, it is simple and easy to implement. Phosphor is deposited on top of the LED surface by spin coating or pulse spray coating method. However, the shortcomings are phosphor itself absorbs the energy and reduces cohesion efficiency. Optimized phosphor particle for lighting and display is quite large. It's around 1 to 10 micron. The size of micro LED decrease. The phosphor layer become uneven. The homogeneity become very bad, and also reduce the luminance homogeneity. Therefore, the good option is quantum dots. Quantum dots can be synthesized by chemical solution process, which is have a high unique properties such as high quantum yield, size-dependent emission wavelength, and also narrow emission line width. Professor Kuo demonstrate full color high quality display by combining micro LED with micro LED and QDs together. To limit cross-talk effect, photoresist mold is fabricated and the quantum dot was deposited on the PR photoresist mold with a clear separation between each other. The DBR Bragg reflector covered above the PR mold significantly enhanced the utilization of UV light and the emission of intensity of RGB QDs. The particle size that used for RGB quantum dots is 9.3, 6.2, and 2.5. This size of quantum dots is smaller than phosphor particles, and the emission spectra are 630, 520, and 450 respectively. So you can see here, these are the different sizes and different color that can produce with the quantum dots. So this can be achieved due to narrow emissions line bandwidth of RGB of quantum dots. Then we can achieve a large color gamut. The next challenges are to transfer or delivery for the micro LED. So for example, small size wafer must be relocated and distributed quickly over wide screen area via so-called transfer technology. Previous techniques transfer chips from a wafer to another substrate one by one or moved multiple chips at a time using chip grabbers. A ball-shaped termed LED ball. It can easily stored in a bottle, dispersed in a solid before use in practical applications, and delivered into via substrate spreading, distributing, and even printing. So this is an example for the transferring process. For the transfer or delivery for the ball-shaped micro-LED, the first method is dispersion. This method, the conversion of an LED chip to a plastic ball with a centered LED chip, like here, can be prepared by the dispersion of polymerization process. Polymerization process for LED balls, ternary systems, chips, monomers, and water. Micro LED chip is encapsulated by monomers, locating micro LED chips in the center of the monomer droplets. For example, acrylic monomers with a different polarity during dispersion polymerization can be achieved by precisely manipulating the interfacial energies of the system, and also inappropriate size distribution can minimize by optimization the polymerization equipment and the processing variables such as baffles, gas, fluids, flow, and agitators in the reactor. The second method for the delivery of the ball-shaped micro-LED is by sieving, which is also known as printing. The sieve template has holes here at the required screen locations, respectively. The LED balls can easily roll to these locations. Sieving is used to position the LED balls in the correct location by sieves. Dispersion can be formulated with additive in order to prevent the formation of voids or agglomeration and even thermodegradation on the screen surface. This is very interesting. This method can be repeated for different kind of RGB using three different sieves. For example, a different shape of sieve. We can focus on only red chips, LEDs, and second sieves only for green, and third sieves for blue. After the arrangement for these all ball-shaped micro LEDs, the dispersion of polymerization process can be removed completely. For example, acrylic polymers depolymerization and decomposition of monomers at moderate temperatures such as below 300 degrees C. That's all for today. Thank you everyone and have a good day.